In the last video, we had developed the second law of thermodynamics, and this video we're going to continue that to get a better idea of what entropy is, and to connect that to a statistical interpretation of things. But we'll start with another restatement of the second law. So here I'll define a perpetual motion machine of the second kind. It'll turn out that a perpetual motion machine of the second kind does not violate the first law, but it does violate the second. Perpetual motion machine of the first kind turns out violates both the first and second laws. The perpetual motion machine of the second kind is a perpetual motion machine that does no useful work. So all it does is just literally run forever. It doesn't do anything. And the restatement of the second law is that it is impossible to build one of these things. So here's a way to think about that. So let's say we built such a device. What would it look like? Well, you'd still, with any engine, you still have to have a hot reservoir, a cold reservoir, and a working substance. So we'd be flowing heat out from the hot reservoir, and we would say, okay, since all we want to do is run this forever, we'll just take the work and we can the work output and hook it up to a paddle wheel or something, do Joule's experiment to do work on the substance in the hot reservoir. However, it's still the case that you have to reject heat to the cold reservoir because the Carnot efficiency of a heat engine can never be equal to 1. So there's no way that you can get the work to equal Q hot. So it's going to be less than Q hot. And so that means that every cycle you will be rejecting heat to the cold reservoir. This means ultimately you'll be dropping the temperature of the hot reservoir, raising the temperature of the cold reservoir, and eventually you'll just come to a halt because there isn't any more heat to flow. So that's a schematic view of that. Now with that, going into doing a statistical formulation, the general treatment of that, it gets very hairy and is beyond the scope of this class. But we can take a look at what physicists like to call toy models. Systems that in principle you could build very simple ones that hopefully clarify the point. So let's just imagine that we have a box. We're going to paint a line down the middle of the box, and we put 4 molecules into the box. That's it. So there's molecule number 1, molecule number 2, molecule number 3, molecule number 4. So it'll always be the case that a molecule is either on one side of the line in the box or the other. So you can say the number on the left side plus the number on the right side in this example would always have to be equal to 4. But how many different ways could we actually arrange all those atoms if we want? Well, let's start making a little table. We have atoms 1, 2, 3, and 4. And let's see, one way we could do it is we could have all the atoms on the left side. So the essential issue here is that they're all on one side, none of them are on the other. So we'll also keep track of what we call the configuration. So this is just the number on the left side, number on the right side. So there's 4 here, 0 here. And there's only one way that we can possibly get this arrangement, so we call this the multiplicity of microstates. This will hopefully make more sense in a second. And the symbol for this is either W or a capital Greek omega. But anyway, this is just counting the number of ways that we can have 4 on the left, 1 on the right, and here there's only one way. All right, how about having 3 on the left and 1 on the right? Well, turns out there's 4 ways you can do that. You could have, say, atoms 1, 2, and 3 on the left, atom 4 on the right, or 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Oops, sorry. 1, 2, 3, 4. So it turns out that there are 4 ways you can arrange this. You can either have atom 1, 2, 3, or 4 on the right hand side. Now the thing is you can't tell the atoms apart. So the only thing we can conclude is when you look in the box and see which side of the line the atoms are on, it is 4 times more likely that you'll have 3 atoms on the left, 1 on the right, versus having all 4 on the left. Okay, well, let's go take a look now at what if we had 2 and 2? How many ways can we do that? Well, we can have numbers 1, 2 on the left and 3 and 4 on the right. And then we'll just leave number 4 on the right here while we move number 3 along. So L, R, L, R, R, L, L, R. So we've got 3 there so far. And then let's see, next one we could do that's different is we can start moving the right one over. So we'll start here, put this guy over there. That would be a new configuration. R, L, R, R, L. Move this atom over. R, L, R, L. And then finally R, R, L, L. And that's it. So all the possible ways you can put 2 on the left, 2 on the right. Turns out that there are 6 ways to do that. And again, we call this a microstate because, again, there's no way that you can draw tiny little 1, 2s, 3s, and 4s on the atoms to know which atom is which. So all we can say is that's 6 times more likely to have 2 left, 2 right than it is to have all 4 on the left. And by the same token, it's 1.5 times more likely to have 2 left, 2 right than it is to have 3 left, 1 right. All right, so we can go ahead and finish out the table here. And this is just going to be symmetric. The next configuration we can look at would be if we had 1 on the left and 3 on the right. And that's just like the 3 on the left, 1 on the right deal here. So we could have number 1 be on the left and these 3 be on the right. There we go. And again, there are 4 microstates of that. So we would conclude that that's just as likely as having 3 on the left, 1 on the right. And finally, just to complete it all out, there's only one possibility left. And that possibility is if all 4 of them are on the right. And there's exactly one way we can do that. Okay. Well, that was a lot. But the idea here is that since the atoms are running around randomly, whenever you look, any of these microstates are equally probable. And that is the big underlying assumption in statistical mechanics. Oops. Let's do a better job with that. There we go. And from this assumption, Boltzmann came up with an expression for entropy. By the way, if you want to calculate the general case for the number of microstates in our left-right system here, if capital N is the number of atoms, and then the number of microstates where you have NL on the left and NR on the right is this, or it's the number of atoms factorial divided by the number of atoms to the left factorial and the number of atoms to the right factorial. And if factorial is ringing a very, very vague bell, you often see it when you do the binomial theorem in algebra class. Just a quick reminder, of that is that 0 factorial is equal to 1. You use an exclamation point for factorial, and you always put it after the number. 1 factorial is also 1. And then 2 factorial is equal to 2 times 1, which would be 2. 3 factorial is 3 times 2 times 1, which would be 6. 4 factorial would be 4 times 3 times 2 times 1, which would be 24, etc. Anyway, this is the how we could count the number of microstates for our left-right system. And to do it in a more general way, where we're not just saying, well, it's either on the left or on the right, which sounds awfully artificial, but there is actually a legitimate system called an Ising gas where something similar to this is happening. And so it is sometimes, there is for one specific case, this is a valid model for describing things, but in general you've got to be do a little more work, and there are these things called partition functions and stuff like that that we don't really need to get into. The upshot of it all is that Boltzmann figured out that for any particular for any particular configuration, you could calculate the entropy. And what he got was that the entropy was equal to the Boltzmann constant times the natural log of the number of microstates. So what does this mean? Well, if we go back and look here for these systems where, say, everything is on the left or everything is on the right, those are low probability systems. And here the multiplicity of microstates is 1. If I take the natural log of 1, that would be 0. So that would be the lowest my entropy could be. On the other hand, the entropy of having 3 left, 3 right would be k times the natural log of 4. And 2 and 2, the entropy of that state would be k times the natural log of 6. And so if you have a system prepared in a low probability state, like for instance, all 4 of the atoms are on the left side of the box, if you were to close up the walls of the box and then open up the box later and take a look, the odds that when you look, all 4 are on the left at that time are rather low. The odds that you're going to have some mix of atoms on the left and the right side is pretty high. And so when you take a look, you're probably going to have be in a configuration that has a higher number of microstates, which has a higher entropy. And so then we say that the entropy will increase. Now, when you're dealing with small numbers of atoms like this, these low probability states, what people often will view as ordered, although being ordered is something that is in the eye of the beholder. This is what gives people the idea of saying that nature evolves towards disorder, is that if you view something like, say, having all 4 atoms on the right side as being an ordered thing, then if you choose to view these states as being more disordered, then yeah, you're evolving toward disorder. But it's really just more accurate to say that you're evolving from low probability states to high probability states. Now, with a small number of atoms, getting back to these low probability states that say all 4 on the left or all 4 on the right, is still kind of good. So I queued up a computer simulation here. Say, well, what happens if you flip 10 coins? You can see, yeah, okay, it's still a pretty good shot of being in any state here. Definitely more likely to have 5 atoms on the left and 5 on the right. But, 0 and 10 are, this is kind of the number on the right. Having 0 on the right or 10 on the right, it's still not totally gone. But certainly there's a good chance of occupying just about anything. Well, we can go ahead and say, well, about 11 atoms, 12, 13, so forth. And in fact, I started doing saying, well, what about 100 atoms? By the time you get to 100 atoms, the odds of having ever anything more than, say, looks like about maybe 36 to the left or 64 to the right is so small that in practical terms it's probably never going to happen. So if you have a state that was prepared where all the atoms are on the left or right side of the box, what you're going to find is that after you let the system evolve, anytime you look, the odds are overwhelming that you're going to find the number of atoms be somewhere in the neighborhood of 50-50 split, with the extremes out to maybe 60-40, 40-60. But everything's going to be mostly clumped right around the 50-50 split. That's with 100 atoms. Let's let this go. All right, so now we're up to 500 atoms in the box. And you can see the odds are overwhelming that you're going to be on a 50-50 split or within a smaller neighborhood around 50-50 percentage-wise. Looks like here maybe you go from about 220 out to about 280. So even though in absolute numbers of atoms, the number of with the distribution is getting bigger, as a percentage of the number of atoms in the box, it's getting closer and closer to always hanging right in the neighborhood of a 50-50 split. Let's let this run up to 1,000 atoms. Whoop. My bad. Doggone it. All right, here we go. So let's take it up to 1,000 atoms. By the time you get to 1,000 atoms, you can see it's ever heading as we have more and more. The odds that you'll be at right around a 50-50 split, in the neighborhood of a 50-50 split, get ever better and better. And the deviation off of 50-50 as a percentage of the number of atoms gets ever less and less and less. So that's just if we have 1,000 atoms in the box. Now, in a real world situation, you're going to be talking about having something on the order of a mole of atoms, so 10 to the 23rd. So by this point, the curve basically will end up looking pretty much like a straight line poking straight up, and anything that isn't in the absolute immediate vicinity of a 50-50 split has probability so small that you'll basically never, ever, ever encounter it. One of the classic problems that physicists learn to say, what do you mean by practically speaking you'll never see it, is we get asked to calculate as a homework problem the odds that if you had one monkey banging random letters on a typewriter, what are the odds that that monkey will bang out a perfect page from Shakespeare's play Hamlet? Odds are really absurdly small. So then you say, okay, let's help that out. Let's make it 100 monkeys banging on 100 typewriters. Doesn't help much. So then you say, okay, what if every single atom in the universe were a monkey banging on a typewriter, and the monkeys are banging on the keys with one keystroke per orbit of a hydrogen atom. It turns out that even in that situation, it would still take, if I remember correctly from when I did it, on the order of about 1,000,000 times the lifetime of the universe if every single atom in the universe were banging out random letters to try to make a page of Hamlet. And then what you get is when you look at things like, a mole of gas, to have, say, all the atoms be on the left or all the atoms be on the right is a probability so much more absurdly lower than a monkey accidentally banging out a page of Hamlet that, although on paper it's possible that all the atoms in a room could potentially rearrange back over to one side, none of us will ever live so long as to see that happen. So that's where we're going with that. So although on paper it's still possible, even here at the 1,000 atoms, it's possible that you could have 800 atoms on the right side of the room and 200 on the left, but the odds are so vanishingly small that you'll never live long enough to see that happen, even if you kept checking in on the state of the box at absurdly frequent intervals. Now, I can't leave a discussion of the laws of thermodynamics without presenting the third law of thermodynamics, so that's what I'm going to go ahead and do now. So in the third law of thermodynamics, again, it wouldn't be me if I weren't giving you at least 2 statements, so I will. One statement of it goes, as temperature approaches absolute zero, the entropy of a system approaches a constant. Or, this is an equivalent statement, it is impossible to reduce any system to absolute zero in a finite series of operations. So what corollary of this is that you can get a system to get as close as you like to absolute zero. For a long time, the record was 0.9 nanokelvin. but you can't actually get there. The gist of that is basically in order to get some system all the way to absolute zero, you would have to somehow reject all the heat outside the universe. But since the universe is all there is, there's no place that you could go and reject the heat to. So you're on your own for remembering the 0th law of thermodynamics, but I can give you a cute mnemonic for remembering the first, second, and third laws. The first law of thermodynamics can be remembered as you can't win. This means you can't build a perpetual motion machine of the first kind. Sorry, no free energy for you. Second law, you can't break even. And that means you can't build a perpetual motion machine of the second kind, because a machine that would just plain run forever without doing anything would be breaking even. But it turns out that no, they all have to come to a halt. And then to remember the third law, is you can't quit playing. So the reason here is that if you were to get a system down to absolute zero, it turns out that that system would have to quit interacting with the rest of the universe altogether. So it turns out that at least at some super, super weak level, things have to you have to keep interacting with the rest of the universe. So you can't win, you can't break even, and you can't quit playing. And on that cheery note, that ends our treatment of thermodynamics, and we will pick up taking a look at oscillations. Have a good one.